Welcome to part 2 of our tutorial on P-N Junction Diodes. Okay, so let us first recall a bit of what we had learned in the previous tutorial. Okay, so we learned the following things that I'm going to show here. The P-N junction is formed, the P-N junction diode is formed by a P-N junction semiconductor and two electrodes, the cathode and the anode. The diffusion gradient across a newly formed P-N junction causes the majority carriers, the electrons and holes, to diffuse through the junction itself. Number 3, the movement of the majority carriers through the junction causes the phenomena of recombination, and hence the formation of the depletion region and the barrier field, thereby opposing the movement of the majority carriers through the junction. Alright, and last but not the least, number 4, the barrier field gives rise to the barrier voltage. Now the energy required by the majority carriers to cross through the junction under the barrier voltage is E, or rather represented by E, which is equals to the product of small e times the VB, where VB is the barrier voltage and here capital E represents the barrier energy. So this term E equals to E times VB represents the barrier energy, and E is the magnitude of the electronic charge. So we learned the following things in the part 1 of our tutorial on P-N junction diodes. So now let's just get on with it and let's see what happens after the P-N junction diode suffers recombination and the barrier field is formed. Alright, so today we move on to the next segment of the P-N junction diode, that is diode biasing. Okay, right, so what is, or rather what do we mean basically by the term biasing? Well, biasing refers to an application of an external voltage across a P-N junction diode. Okay, so imagine this is a P-N junction diode, right? So before moving on through this topic, let me just say that why do we need to bias? It's basically because we know that in order to cause the current flow through a P-N junction, when the barrier field opposes the motion of the majority carriers through the junction, we need to apply or impart an energy of E, which is the barrier energy, to our majority carriers so that they could cross over the junction and flow. So in case of diode biasing, we can apply an external voltage, or rather, in order to make the majority carriers cross the P-N junction under the presence of the barrier voltage, we need to apply an external voltage supply, which could be a battery or any kind of electrical source. So we apply an external battery, and by that we impart kinetic energy to the majority carriers so that they may cross the junction. So this is the need of biasing, and in case of biasing we have two modes of biasing. That is, the first one is the forward biasing mode. Okay, in case of forward biasing, the diode is connected to a battery, that is the external voltage source, in the following way that I'm showing in the diagram. That is, the anode of the diode gets connected to the battery positive terminal, while the cathode of the diode gets connected to the negative terminal of the external voltage source or battery. Okay, so under this condition, what happens is that the external voltage being applied to the diode, causes the reduction in the depletion region of the diode. So imagine that this is a P-N junction diode, okay, which is the P side to the left and N side to the right, and let's say this blue colored dotted line represents the depletion region under unbiased condition. Okay, so this is the depletion region under no bias. Okay, so this is the depletion region size under no bias, and now after biasing is done, I mean after the diode has been subjected to forward biasing, then a change occurs in the depletion region width, right? So the whole picture becomes somewhat like this. The depletion region gradually narrows. Okay, so depending upon the amount, or rather the magnitude of the external voltage applied, all right, the depletion region narrows down and gets thinner and thinner as the external voltage across it is increased. So if we just say, for example, assume that the depletion region width in case of no bias condition is W, then under the forward bias condition the depletion region width becomes small w, where capital W is greater than small w, which means the width has in a way decreased. If this was the earlier depletion region, then the width decreases to a very narrow space. Okay, so due to the decrease in the width of the depletion region, the majority carriers, all right, are now able to move towards the P-N junction better than under no bias condition. And apart from that, the external voltage that is applied across the diode imparts sufficient kinetic energy to the majority carriers so that they can surmount the energy barrier and cross over the junction using this amount of energy as required. That is, they gain an energy equal to the barrier energy, and with that they surmount the voltage barrier and cross over the P-N junction, thereby leading to a net flow of electric current through the P-N junction from the P to the N side. Okay, so there it goes. Right, now what happens in case of the other type of biasing? So here we have the other type of biasing mode that's known as the reverse biasing mode, right? In case of reverse biasing mode, just the opposite happens. So if this be our P-N junction diode, okay, it is connected in just the reverse way in which the forward biasing is done. That is, the anode of the diode is connected to the battery's negative terminal, while the cathode of the diode is connected to the battery's positive terminal. As a result, the anode of the diode has a negative voltage and the cathode of the diode has a positive voltage. Under this condition, the depletion region width in a P-N junction diode increases. Okay, so if this be the P-N junction diode which we're discussing about, then the depletion region, okay fine, let this be the width of the depletion region under no bias condition. Okay, or rather let's just take, for example, we take the reference of the previous diagram of the P-N junction diode under no bias condition, whose depletion region width was W, and depending upon that, upon reverse biasing, the depletion region width increases so that the new width, if it's, let's say, um, if the new width, let's say, is a small w in this case, then small w will be much greater than capital W under reverse biasing conditions. So what happens is, basically the depletion region undergoes expansion, and as a result of this phenomena, the majority carriers find it even more difficult to cross the depletion region. Okay, and also due to the fact that this external voltage applied across the diode now aids to the barrier voltage and thereby increases the energy barrier, which becomes, which becomes in this case EB dash equals E times VB plus V external. So the voltage barrier, or rather the energy barrier across, which is required for the majority carriers to overcome, increases under reverse biasing conditions, as due to the barrier voltage, the effective barrier voltage increasing upon the application of the external voltage. Okay, so based on these two types of biasing modes, we can say that the diode under forward biasing condition is able to conduct a current. Okay, so a net current flows through the diode from the P side to the N side under forward biasing condition, while under reverse biasing condition very little or no current flows through the diode. So the current through the diode is approximately zero under reverse biasing condition, except for some very negligible minority carrier current that's generated inside a diode due to the diffusion currents and impurities inside. Okay, as was discussed in our tutorial on semiconductor physics. So only the minority carrier current, represented by I0, okay, so minority carrier current is what that can flow inside a reverse biasing diode. Okay, now this being of the order of, let's say, microampere range, we can just neglect it, and basically looking at the reverse biased condition, the diode doesn't conduct any significant amount of current which can produce a certain type of electrical work. So these were the two biasing modes of the diode, and depending upon these two modes discussed, we have our diode characteristic curve. So the y-axis represents the forward current, or rather the current through the diode, okay, in both directions, and the x-axis represents the voltage applied across the diode. Okay, so on the right hand side, this one, we have the forward diode characteristics, and on the left hand side we have the reverse diode characteristics. So imagine, in case of the forward characteristics, imagine that the diode is in the forward biased condition, and due to that, when the diode is in the forward biased condition, its characteristic looks somewhat like this. Okay, so I shall discuss, or rather explain, the details just in a short while, but before that I would like to tell you about the cut-in voltage over here. So there is a certain amount of voltage that needs to be overcome in order to let the diode conduct significant amount of current in the under the forward bias condition. Now this particular voltage that needs to be overcome is known as the cut-in voltage, okay, which is, this is the cut-in voltage. Now the cut-in voltage is approximately similar to the barrier voltage, and the value of V cut in is about 0.6 to 0.7 volts in case of silicon, and 0.2 to 0.3 volt in case of germanium. Alright, so when the diode is in the forward biasing condition, we get the forward characteristics. Upon increasing the forward voltage across a diode, and the diode current begins to increase but very slowly. Okay, so there is no significant change in the amount of current flowing across the diode until the forward voltage exceeds the cut-in voltage, and when the forward voltage exceeds the cut-in voltage, the diode current significantly changes, and upon the application of higher voltages, the current through the diode, or rather the diode characteristics, becomes a vertical straight line. That is, the current to the diode increases exponentially. So we can regard, or rather we can therefore call this characteristics as non-linear. Therefore we understand that the diode is a non-linear device. Okay, now in case of the reverse characteristics, what happens is, upon the application of reverse voltage, or rather when the diode is reverse biased, then if we just go on increasing the reverse voltage across the diode, then the reverse, or rather the minority carrier current, or rather the reverse saturation current, which is also the other name for minority carrier current, begins to increase, and it begins to increase up to a certain point, which is known as V gamma, is a short form of showing it, and this is known as the breakdown voltage. Okay, so when the voltage, or rather the reverse voltage across a reverse biased P-N junction diode reaches the breakdown voltage, the junction, or rather the P-N junction that has the ions inside it, okay, the voltage becomes so high that the electrons from the ions are just torn apart, and those of the minority carriers that are present on either side that constitute the minority carrier current, they gain sufficient kinetic energy to even knock electrons out from inside the ions, okay, and thereby constitute a huge amount of current, as you can see here. So in this state, or rather when the diode enters, or rather crosses the breakdown voltage, it enters into a place in the characteristic termed as the breakdown region, where the reverse current through the P-N junction diode, or rather through the reverse biased P-N junction diode, increases significantly, even with minute changes in the voltage applied across it. So at that time, the diode junction, upon the conduction of severe amounts of reverse current, breaks down in most of the cases, and the diode suffers a burnout. So based on the characteristics that we have here, we can put forward an equation that would give us the instantaneous amount of current through a diode. So here I0, so here I represents the instantaneous current through a diode, while I0 represents the amount of reverse saturation current through the diode. So this equation would be written somewhat like this: e to the power EV by eta kVt minus 1. So here, as we can see, that I represents the instantaneous current, okay, the instantaneous current through a diode. This represents the reverse saturation current through the diode. Okay, here V represents the voltage applied across the P-N junction diode, voltage across diode. Okay, eta is the multiplication factor, which is 1 for germanium and 2 for silicon. Okay, Here Kb represents the Boltzmann's constant, and T is the temperature at which the diode is operated. Okay, so T represents the operating temperature of the diode. Operating temperature of the diode. Right. So that's the equation required to calculate the instantaneous current through a diode for any given voltage across it under both the forward and the reverse bias conditions. So summarizing the above facts discussed about the biasing and the characteristics of a P-N junction diode, basically this is the amount of information required, or rather used by circuit designers in order to incorporate a diode into an electric or electronic circuit. Okay, so that's pretty much from the diode theory, and till then I hope you've liked our tutorial, and see you next time. Until then, it's goodbye from now on. Okay.